So, Ina pit crater on the moon is a really, really intriguing feature discovered more or less in the Apollo 15 data. It was kind of hidden from view by a BIMAP bubble in lunar orbiter images. So it was discovered in time of Apollo 15, and it's really enigmatic. But let's start with a general characterization of volcanism, because this feature is surprisingly young looking. And the question is it really young looking, and what does that tell us about the evolution of volcanism on the moon? So we know that the bulk of lunar basaltic volcanism occurred during the 3.9 to 3.1 billion year period. That's this period in here. We also know from meteorite ages that it also has occurred as young as 2.9 billion years ago. And there's evidence from stratigraphic relationships and impact crater size frequency distribution for this red unit here that it occurs as recently as 1 billion years. So an enigmatic surface feature, Ina, may represent much younger volcanism, perhaps out even to almost the present day. That's this feature here. In a really interesting paper in 2014, Sarah Braden and her colleagues, mostly at ASU, using LROC data, documented a whole series, 70 of these small topographic anomalies, as they call them irregular Mare patches, or IMPs, and they had dimensions between 1 and 5 kilometers. They occur on the lunar near side in the Maria, and they contain irregular morphologies and textures similar to Ina. This is Ina here, and you can see the textures are very, very similar. In addition, the floor of these features is often optically immature, meaning that, in fact, that it looks relatively recent. So that would be like Copernicus crater or Tycho crater, optically immature, as Carly talked about earlier. So few superposed craters that are larger than 10 meters in diameter. So that's really saying something. That must mean they're also young. The crater distributions of the three largest irregular Mare patches is, in fact, less than 100 million years. And here's the size frequency distribution curve. So, of course, it's really hard to date things using small areas because you're statistically underrepresenting, the sample. And so these are the three largest areas, and they are, in fact, of the ages. This is Ina right here with the age of 33.2. Sosigenes right here, which has an age of 18.1, and Ina itself with an age of, let's see, did I just do Cauchy 5 with an age of 58.3, all less than 100 million years old. So this is pretty amazing, because if in fact those are the ages, the morphology seems consistent with small basaltic eruptions, and if these occurred significantly after the time that volcanism apparently ceased in the Mare, this would have incredible implications for the thermal evolution of the moon. How do you keep the interior warm that long? How do you generate enough overpressure to actually get these things to the surface? And how can you get them to be in such small volumes and quantities? So this is really amazing. Okay, so this of course draws our attention to these, and we address the question: how did these form? Under what environment? What kind of situation? What's the detailed evidence for the impact crater size frequency distribution and the morphologies? This is a diagram I put together, which is an interpretation of what they say in the paper. So this is Ina, and this is a sketch map of what it looks like. There's two units, an uneven unit, which Braden et al. Interpret to come out first by a dike feeding emplacement event. And then the second stage is a smooth unit, which comes out through that and is emplaced on the top of the surface. And as you'll see in a second, these things do look like they're morphologically superposed from a general point of view, as you can see here. So in order to investigate these further and ask the question, what are the characteristics of Ina in detail, and what's the evidence that it is so young? This is a critical issue. Let's take a look first at the characteristics. This is a perspective view, if you will. It's 2 by 3 kilometers, 50-meter deep depression with low mounds, you can see here, similar in appearance to surrounding Maria, but in fact rising from this disrupted floor. And you can see the optically immature areas in here, these very bright areas around the margins and patchiness in the interior. So what do we want to know here? So we need to explain the geological setting. We need to understand the topographic setting. What can that tell us? We need to look at the unusual morphology as is up, and then explain the optical maturity and the very young crater size frequency distribution ages. Braden et al. Explain all of this by these extremely young eruptions. So let's go and examine those in more detail. Let's start with the geological setting and the topographic setting. Brent Gary and colleagues have really nicely characterized much of this in a paper, I believe it was at Icarus. And we've also taken a look at this with even newer data sets. And so this is where Ina is. Here's Mare Imbrium, here's Mare Serenitatis, and this is Mare Peporum. It sits pretty much in the middle there. This is a topographic map, and you can see there's a broad rise in here. This is sort of the Imbrium sculpture coming away from Imbrium, which is superposed on Serenitatis. But if we tune in on this, we can actually see the topography here. And Ina is located here. It's a rise on one of these inter-Imbrium plateaus here. And if we tune even further in, we can see that Ina, the unit here, actually is on top of what would pass by any circumstance as a shield volcano. Okay, this is just like the ones that Brian Day was showing in Hortensius and elsewhere. There's hundreds and hundreds of these on the moon. So that's interesting. Ina sits on top of a shield volcano. It is almost virtually the summit pit of a shield volcano. So that's fascinating. And Ann Gifford and I did a study many, many years ago in which we took a look at all these kinds of small shield volcanoes, and we compared the base diameter to the summit crater diameter. And in fact, Ina's pretty much on that line with the other ones. It's at the large end in terms of the size of the shield volcano, a little over 20 kilometers. And you can see we can do topographic maps of this, we can look in detail, we can look at the slope data, and it's all consistent with this kind of situation with the summit crater on top of a shield volcano. Okay, so this all tells us then that we're dealing with something that's not just out by itself, but it has something to do with volcanological activity. We've dated these units here, and they come out about 3.5 billion years old, so this is really old volcanism. And the summit pit crater is, in fact, where the very, very young deposits are found, according to the Braden interpretation. Now, the problem is, how do you have a summit caldera that sits around for 3.5 billion years and then waits to erupt small deposits in the middle? This is a problem for me as a volcanologist. It's very hard to keep the same dike open for decades to centuries, let alone billions of years. So let's just keep this in mind, this setting, et cetera, and take a look at the unusual morphology. If we take a look in the interior then, this is a perspective view of that interior, and you can see the mounds and the intermound areas in here. And one of the things we find, if we take a look at this in a topography reconstruction, that the central part, this is the same feature, okay, the same view, the central part is depressed relative to the mounds in the surrounding areas. Well, in a pit crater, this gives us some clue as to what's going on. Oftentimes in the middle of these pit craters, you'll get subsidence due to withdrawal of the magma down in the interior. Sometimes you get fluctuating eruptions, eruptive phases that bring it up, take it down, et cetera, et cetera. So this is also important information, and it brings us to examine a number of terrestrial analogs, and the most impressive one was a highly gas-rich eruption in Kilauea Iki in 1959, and this was amazing. It had one of the most spectacular fountains because it was so gas-rich. So this is a view of the actual eruption. The eruption came out, it filled this crater here several times. It drained back down in, filled the crater again. Meanwhile, gas was being exhaled through these eruptions, et cetera. And so we have a really, really good record of this, okay? So when we go in and look in detail, we can see that was where the eruption was coming from. You can see the drained lava lake here. You can see the rim, cooling rim around the edge. You can see a lot of kapukas, that is previous topography from the previous phases that have been left in the middle. And when we take a look at this, we can kind of like do a reconstruction based on the Geological Survey's excellent documentation of these. So what happens with pit crater lava lakes is you have pre-existing topography from early eruptions. You have a vent, the lava comes out, fills it up, and indeed produces a thermal boundary layer on the top that is the cooling boundary layer, and then starts to cool. But typically what happens is the lava recedes back down into the vent because so much degassing has taken place, and you end up draping this thermal boundary layer over the surface and getting voids from drainage tubes that go back down into the vent. So you produce something that's extremely void rich. That's a critical issue in these things. And if we take a look and wander across the surface here, let me show you how that works, we see a lot of evidence for what I would call macro porosity, okay? So this is the deformed thermal boundary layer, okay, that's draped over the kapukas, and you could fall into this and never get out, okay? There's a lot of void space. You can see it in here, the draping boundary layers. So here's a whole series of examples here of these plates that have been draped. There's a lot of macro void space in here, okay? And when we look in detail, here's one of those areas here. Look at people for scale here. There's huge amounts of void space in the subsurface because of the deflation of this. And maybe that gives us a clue as to what's going on. There's also micro porosity, I would say. It's not totally micro, but it's micro in the sense of what we're looking at here. So these are extremely vesicular lavas here. This is the upper boundary layer. that's being draped over, and it is really vesicular. We know that from all the records of drilling. The drills will go in through this very 20% vesicularity and more, and it'll... Did I just hear a duck? Okay. I think that's a phone call for you, actually. So you see that, you see the void space, so we have several different kinds of viscosity here. What about the optical maturity? So one thing we can say here with this morphology is maybe it has something to do with this being a lava lake, and maybe macro and micro porosity might be a factor in explaining what we see. So when we take a look at the drained lava lakes, extreme macro and micro porosity, so if we think about what's going to happen when you start having a regolith on top of this on the moon, this is initially drained lava lake. It's just what we were talking about. You have the kapukas, you have plates draped over these, lots of draping of plates and lava tubes and both macro and micro porosity. And when you start developing a regolith on this, well, obviously you're going to break it up, drain a lot of the finer material down into the void space, both macro and micro. You're going to be forming regolith and very vesicular material. And so in principle, we think that a lot of the regolith development would be draining down into the interior, and you would, in fact, get differential regolith development based on these two situations, with a lot of the regolith being drained away all the time from seismic shaking and other types of things, and that would lead to maturity, constant maturity of the surface. So if we think about the very young crater size frequency distribution ages, how might we explain these? Well, if we think about the same type of effective macro and micro porosity, think what happens when you impact into a very vesicular material. You're not going to get the same kind of size frequency distribution that you get when in fact you develop this in a solid basalt. So if this is significantly laden with macro and micro porosity, impacts into this are not going to look like they do elsewhere. You're going to have material that's drained back in, you're going to lose craters, you're going to have slopes, macro and micro slopes that are going to modify the surface, and it could keep it looking relatively young and get rid of a lot of craters or have them hard to recognize. And in fact, the other part of it is that foams, that is the very viscous material, foams will be, in fact, a major factor here. Just like with Kilauea Iki, it's a very foam-rich lava. What happens when you extrude that foam out onto the top in these mound-like features, for example? Well, in fact, if you impact into that, you don't create the kind of craters you're used to in solid basalts. This is an impact into a pumice, and it's about, about 20 centimeters across here. You just get the impact crushes the material. It does not create big craters. If this was in a basalt, it would have created a crater like this, but instead it makes a hole and compresses things. So if we have this macro and micro porosity, it's going to completely disrupt the impact crater size frequency distribution that we have for the basalt. So our idea is then, when we take a look at this, we're dealing with a summit pit crater, a summit shield volcano pit crater. This is typically what happens. You get drainage of lava lakes, you get ultra-vesicularity at macro and micro levels, and you get foams, etc. We think that this could have something to do to explain the optical immaturity of the surface and also the very young crater size frequency distribution ages, because craters are not forming in the same way. They're forming at diameters that are much less than they would if they were in solid basalt. So we're exploring this further for Ina and also the other two areas. We think that we can get the ages back up to something of the order of the same age as the surrounding area, the area surrounding Ina, which is about 3.5 billion years. So this may mean, in fact, that the bulk, the Ina could be formed at about the same time as the bulk of the volcanism here, where the shield volcano itself forms. Thank you very much.
Any questions for Jim at all? We have time for one.
Throw him the ball. Throw him the. Yeah.
You don't want me to throw it.
I'll throw it.
I'll hit somebody else.
You've mentioned the seismic settling or shaking a few times. Have you modeled this or done any laboratory experiments to try to quantify how that effect might be, or are there any field sites where there might be some testable measurements we could take to see how significant that effect could be?
Yes, there are a number of papers that have, I have not done that myself personally, but there is a literature on this. A number of people have looked at it in terms of regolith development in general, and also, just essentially there was a lot of work done in the early days where you were trying to figure out actually what the density of the regolith was. sort of simple model of regolith formation. It did not take into account the seismic shaking, gave you an underdense relative to a denser thing. But if you have all this macro and micro vesicularity, we think that's a possibility that even till today you could drain material down into the interior. Experiments would be good. I mean, I think we can frame experiments better now than we were able to in the past.
We could measure before and after an earthquake at a spot, for example, and see what
That's
changes.
right. Yeah. What the magnitude? Let's see. What is kind of known is the magnitude of moonquakes, impact quakes, related to the diameter of the crater, and because the energy partitioning is kind of known. And so we've looked at okay, how much if we take the frequency distribution of craters around it, how much is that going to produce? And plenty, over 3 billion years.
Sorry, we're going to have to move on. If you could hold your question. Thank you.